Hey there, and welcome to Raylene Math. In this video, we're going to take a look at freefall motion in one dimension. This means that we are going to be applying some functions, specifically constant, linear, and quadratic functions, to the physics, kinematics, concepts, and equations. Kinematics refers to moving, as in the word cinema, which is moving pictures, and freefall in particular means that the only force acting on an object is gravity, the attraction of the Earth on the object. Specifically, we are going to get into the motion side and not the force side through Newton's second law, F equals ma. So without further ado, let's consider that we toss an object straight up into the air and there's no air resistance acting. And what happens to that object? What happens to its velocity? What happens to speed? What is speed? These are all sorts of questions that we get a bit mixed up, even though we may have seen some formulas and done pretty well in physics. Let's take a look at the exploration, starting with number 1. An object is launched straight up into the air from an initial height of 90 meters. Tell me about the motion. Well, really, all I'm looking for here is the object goes up and it comes down. We really just want to make sure we understand this scenario. The reason it goes down, of course, is because of gravity. In part number 2, it says 1 second later the object's velocity has decreased a bit to 60 meters per second. Well, if the velocity has decreased and it's 60 later, then it must have been more earlier. That's what it tells you. So the velocity decreases, and we can write that as saying that the change in velocity is negative. And we can say that velocity initial is greater than velocity final. So the velocity at 0 seconds is greater than the velocity at 1 second, which was 60 meters per second. But it also tells us then that the acceleration value, which is equal to the change of velocity over the change in time, must be negative, because the time value moving forward is going to be positive. So we're talking about time increasing, therefore time delta t is going to be positive. Okay, in number 3 it says after launching, and then ignoring the effects of gravity, the only force acting on the object is gravity, so the object is said to be in free fall. When specifically will this object be in free fall then? Well, consider that we toss the object up and it comes back down. So it's being launched and then the object is landing on the ground. And so we're going to say that the object is in free fall for an open time domain of time launching, which is usually 0 seconds. That's when we start the stopwatch of the experiment, until the time of landing. Because at landing, we are going to have the ground applying some kind of contact, or what we call a normal force, perpendicular to the object from the surface. And furthermore, at launching, we are going to have some kind of launch object, so some launch force, like a rocket propulsion or something. So there's going to be a launch cause, which is going to be some force. And so we actually don't want to include the time of launching and landing because other forces are acting. So I'm actually going to put open circles there to indicate that those time values are not included. And then in number 4 it asks, or it says, because of Newton's second law, F equals ma, since the force on the ground on the object is constant, the acceleration is also constant. That's because the mass is constant. So if we assume that we are on some fictitious planet called steady, it's just called steady because it means it has a constant acceleration. And if the acceleration on this fictitious planet is negative 20 meters per second squared, what does that mean? Well, when we think about the number negative 20 meters per second squared, we might try to relate it to speed or velocity, which is measured in meters per second. But it gets a bit confusing to do that because the units are different. When we measure velocity or speed, we get meters per second. But we may try to break it up as negative 20 meters per 1 second squared. But we don't have any physical meaning for a second squared. So instead, we refer to it as negative 20 meters per second per 1 second. And if we recall what we said earlier, that acceleration is equal to the change in velocity over the change in time, well, then we can start to see that since the change in time is positive, because time is increasing. That means that the velocity is decreasing by 20 meters per second every 1 second. Let's write that down. Therefore, a equals negative 20 meters per second squared implies that this is v final minus v initial, or v earlier minus v later. V later minus v earlier, rather. So the velocity decreases by 20 meters per second every 1 second. Now we also know that, because we are on planet steady, that the acceleration is constant. And since the acceleration is constant, that means every 1 second that passes, another 20 meters per second of velocity is lost. And what we can say is, if this is our velocity graph, and as time goes on, if the velocity loses 20 meters per second for every 1 second, and that's happening at a constant rate, that we end up getting some kind of linear function for velocity. In fact, these ideas of similar triangles, negative 20 meters per second per 1 second, we can multiply by 1 in the form of 2 over 2 seconds to get a loss of 40 meters per second in 2 seconds. And then we can multiply that by another constant, say 10 over 10, which is 1. And we can get negative 400 meters per second is lost every 20 seconds. And so we can see that we get similar triangles here for different bases, where the base of the red triangle represents 1 second, and the height of the one red triangle represents negative 20 meters per second. So we can start to see this idea of similar triangles belonging to the notion of linear functions, and therefore constant slopes or constant rates. Okay, so now let's say that we've collected some data. We're going to take a look at working numerically from this perspective for now, so that we can bring things in and look at the rule of 4, which means that we're going to look at things graphically, numerically, algebraically, as well as verbally. So verbal, numerical, graphical, and algebraic. Why don't you pause the video and see if you can fill in some of the table on your own. Basically what we have is a relationship for time and height. We have another relationship for time and velocity, and we have another relationship for time and acceleration. Okay, I'm going to continue. One of the definitions of the problem was that we have a constant acceleration. So as time goes on, from 0 to 9 seconds, the acceleration is constant. And we know one time has an acceleration of negative 20, and so all acceleration values are negative 20. We also unpacked what that negative 20 meters per second squared means. It's a loss of 20 meters per second of velocity every 1 second. And so we can look for a time difference of 1 second, say between points A and B, and know that the velocity will have decreased by 20 seconds. And therefore, at point A, the velocity had to be 80, so that a decrease of 20 takes us to 60. We also know that by point D, the velocity has decreased 6 1-second times. And so multiplying by 6 over 6 gives us negative 120 meters per second over 6 seconds. And so we have a loss of 120 meters per second from the initial 80 meters per second. And so 80 meters per second minus 120 meters per second tells us that the velocity is going to be negative 40 here. And similarly, we lose another 2 times negative 20 meters per second going from point D to point E, which is a loss of another 40 meters per second for a total of negative 80 meters per second. From point E to E, 1 second elapses, so we lose only one negative 20, or we lose only one 20 meters per second amount, giving us a velocity of negative 100 at point F. It's a little bit harder to know what's going on for the height values, so maybe we'll wait to see once we have some equations what's going on here. But we do know that at point C we've reached the maximum height. The maximum height is the instant at which the particle stops increasing, where velocity is positive, and starts decreasing, where velocity is negative. And the boundary between increasing and decreasing occurs when there is a sign change in the velocity. And so we have, at that point, that the velocity is 0. And from here then, we can see that there has been a loss of 60 meters per second from point B to C. That's how we went from 60 decreased down to 0 meters per second. And so if we have lost 60 meters per second, that would take 3 seconds at a rate of negative 20 meters per second every 1 second. So we know that from point B to point C, 3 seconds must have elapsed. And so if we take advantage of that, we add 3 seconds onto 1 second, and we get 4 seconds at point C. And so now we can start to use this information to plot what I like to call the ordered quadruples on the height versus time graph. So this is actually the y-coordinate axis measured in meters, and this is the time coordinate axis measured in seconds. So we are going to see these ordered quadruples where the ordered pair, time comma y, represents the width and height of the point. But at each point, A, B, C, D, E, F on the graph, we have 4 pieces of information associated. And so those 4 pieces of information are time, height, maybe I'll use H for height instead of Y. And then we have velocity and we have acceleration. And the units are given in terms of seconds, meters, etc. So we can fill in some of the information that we just got from the table. First and foremost, we know that all the acceleration values are negative 20, and they will go in the 4th slot in each ordered quadruple. Negative 20 there. So what I'm doing here with these ordered quadruples is just using the table values on a graphical format instead of in a table format. We can also go through and put in all of our 6 green velocity values. So the 60 was given, but we are going to put in 80 meters per second, 60, 0 meters per second. And this is convenient if we connect the fact that the tangent slope here we have a horizontal line, so its tangent slope is 0, and the tangent slope represents the rate of change of the output with respect to the input. And the rate of change is a slope measured in meters divided by seconds. And so meters per second with the value of the slope of 0 says that our velocity at this instant is 0 meters per second. Now we found that by recognizing we recognize that there is a change in the velocity from being positive to negative when the object reaches its max height. So this is just another interpretation of that. Okay, so we can plug in the rest of the values, negative 40, negative 80, and negative 100. And then it remains that we have to figure out we have one more value here. This is an initial time value, and that initial time value is just corresponding with launching at time 0, so I'll put that in. And then we have 2 unknown values, 3 different heights. These are not going to be so easy to figure out, so we'll have to wait until we have some equations to do so. Okay, the next question asks, for what times is the object in free fall motion and why? So we were talking about the object being launched, and here we're saying the launching occurs at point A, which corresponds to time 0, and we have a landing. The landing means that there is a connection to the ground. And as soon as we have the ground, we have a normal force which applies upwards or perpendicular to the surface on the object. And so this force is second to the acceleration force and the gravity force, and gravity is no longer the only force acting. Similarly, whatever is causing the launch is a force, and we have to remove that time value from the time domain for free fall. So time is going to be contained in this case from 0 to 9 seconds, which is the domain for free fall motion. All of the different free fall or kinematic quantities, position, velocity, acceleration, have this same domain. So for all free fall equations, the domain in this example will be from 0 to 9. Okay, the next question is asking to talk conceptually about motion. This is for you to write on your own. It would be a really good idea for you to pause the video and to figure out when you think the object is going up, when it's going down, when the velocity is positive, when the particle is speeding up, and so on. The work we've done already may help to clear up your misconceptions if you had any, but really try to answer it based on your pre-existing understanding of motion. I'm not going to fill anything in here because my conceptions have been cleared up by what I'm about to show you. So now let's move on to number 9. We're asked to consider the acceleration versus time function and write the equation for it. Well, we know that the acceleration on planet steady is constant, and so even though we might want to write it as a function of time, it doesn't depend on time. And so in this case we have a constant function which is the simplest type of polynomial. This is true because time, or I should say acceleration, is not dependent on time. Acceleration doesn't depend on time. And so we can easily come up with a graph for this function. If we scroll ahead, let's take a look. We've got some graphs coming up in number 12. And so let's actually put our acceleration equation, a of t, or simply a equals -20. We're going to have time along the horizontal axis measured in seconds, and we can plot the graph here on our time domain. Don't forget that we have a domain of t contained from 0 to 9. And so if we plot that -20 for 9 seconds, we have a horizontal line that looks like this. Okay, let's go back. The next question is asking us to come up with, in number 10, the velocity versus time function. So we have some information about the velocity. We have a full table of values for the time. So if we just focus on this time as the input x and this velocity as the output y, you should be able to notice something about the values. In particular, as the time increases by 1, the velocity decreases by 20. If the time increases by 3, the velocity decreases by 60. If the time increases by 2, the velocity decreases by 40. And so we're seeing this constant slope relationship. We have a linear relationship for the velocity. So we can write that linear relationship in any way we like. Just checking I used green here. And so you could use y equals mx plus b, where y in fact represents velocity and x represents time. Now we know the slope. The slope of the velocity graph is acceleration. And so slope of the velocity time graph, I'm just writing it as a subscript, equals acceleration. And the constant acceleration, the constant slope we have is -20. We also have the y-intercept because we know at time 0 we have a velocity value of 80. And so we have all the information that we need, and we can write the equation of the velocity. I'm just going to translate this. Velocity equals -20 for the slope times t for the input variable plus 80. And we can use that information. We could write it as v of t or simply v, and we can go to number 12 and write the graph. Let's sketch the graph. The velocity is equal to -20 plus 20t plus 80 on a domain from 0 to 9. So we have an initial velocity of 80. We have at 9 seconds, 9 times -20 is -180, and -180 plus 80 is -100. And if you just confirm the table of values, we had that -100 in the table of values at 9 seconds. We can also find the time intercept here if we substitute velocity on the left with 0, and we end up getting t is equal to 4. So just to make sure that the graph is reasonably accurate, we can plot that. Again, this is time measured along the horizontal axis in seconds. And then we can go back up. Part B of this question says to identify the meaning, the units and the meaning of the two coefficients. So the coefficients are, as we said, The m represents the acceleration, and the b represents the initial velocity. So with that in mind, we have some units for velocity of meters per second. We have the units of acceleration, the -20, in meters per second squared. But then we're multiplying that by the units of time, and then we're adding that to the units of 80, which is for initial velocity. And so we're getting something measured in meters per second, added to something in meters per second, and we're getting that the units make sense. Meters per second line up with meters per second. So we have like terms, and this is a meaningful set of data or values inside the equation. The next question says to consider the height versus time function and to determine the quadratic equation. Well, if we want to come up with a quadratic equation, we have some different function or equation models we could use. We could use the function model, y equals ax squared plus bx plus c. Or if we have the vertex, we could use y minus k equals a times x minus h all squared. Or if we have both x or time intercepts in this case, we could use y equals a times x minus root 1 times x minus root 2. Now we do have the vertex, so we can use this middle form, and if you recall, the vertex was located at 4,250 meters. I believe that's the case. Let's just look. Now this was data that we're saying was collected. We do have the 4 here to go with 250, so I'm going to put that in. And so we have that point, which immediately gives us 2 of the 3 unknowns. We now know the equation so far is y minus 250 is equal to a times x minus, the h value is the time of 4, and that's all squared. Now in order to solve the unknown a, we need another point on the time height graph, and we have a point, the initial one given was 0, 90. So we'll use that point and substitute into the equation. So let's sub 0, 90 in for x and y. So we get 90 minus 250 is equal to a times 0 minus 4 all squared. We get negative 160 is equal to 16a, and we can see that a is equal to negative 10. A word of caution here. The value of a in each of these equations is just meant to be the coefficient of the quadratic term. This a does not necessarily mean acceleration. So just because we've chosen to use a letter of a doesn't mean that it's always going to represent acceleration. So now that we have that equation, we want to write the quadratic equation. We can do that. But the quadratic equation form that we have so far, y minus 250 equals negative 10 times x minus 4 all squared, or if we replace y with height, minus 250 equals negative 10 times time minus 4 seconds all squared. Still doesn't mean a whole lot, except this 4 is the time to maximum height, and this 250 is the maximum height. We still want to relate it to some of the kinematic quantities, the velocity and the acceleration. So to do that, we're going to expand this equation and see if we can't use some more dimensional analysis. So we're going to do part B, identify the units and the meaning of the 3 coefficients. So in part B, when we expand, we get h is equal to negative 10 times t squared minus 8t plus 16, and then add 250. From here, we get that h is equal to negative 10t squared plus 80t, and then minus 160 plus 250 will be plus 90. So from here, if we take a look at the units, we know that each term has to have units of meters per of simply meters, because this is the position graph. So here's a term, here's a term, here's a term, and here's a term, and each term must be measured in meters. Okay, so let's take a look. We've got meters for height, and then we have time squared is going to be seconds squared, and we need something multiplied by that to give us meters. And so the units that have to work are meters per second squared, so the second squares reduce. In the next term, we have something multiplied by seconds for the time. And so the 80 must have units of meters per second. The last term is just a constant, and that constant has to be measured in meters. So we now know that from the A, B, and C terms, therefore A is equal to, I'm going to put A in quotation marks, A is equal to negative 10 meters per second squared, B is equal to 80 meters per second, and the C is 90 meters. And so from here we can go back and take a look at the graph and the table of values, and we can be reminded that the 90 meters came from the initial position, the initial height. Meanwhile, the 80 meters per second came beside it from the initial velocity. And we don't have negative 10 meters per second squared anywhere because the constant acceleration on planet steady is negative 20. So we might make some connections here that definitely this 90 is equal to the initial height, this 80 is equal to the initial velocity, but this negative 10 meters per second squared, although it carries the units of acceleration, it's not the negative 20 meters per second squared value we were looking for. Well, we can kind of get to the answer without fully understanding why, that this is going to be half of the acceleration due to gravity. And here I'm going to use A without quotations, where this does actually represent acceleration. When we see calculus, derivatives, and antiderivatives, we will understand the presence of this 1/2 coefficient in better detail. But for now, we have our quadratic equation, and we can account for all of the units. So the next thing that we're asked to do is to complete the table for the missing height data using the best equation form. So we can use either the expanded form or the transformational form in red. I'm just going to put a box around that equation, whichever one is going to be easiest for us to use. So going back up, I'm going to write the equation of the quadratic just a little bit lower here, and we have that the height equation is given by negative 10t squared plus 80t plus 90, or we could use h minus 250 is equal to negative 10 times t minus 4 quantity all squared. So depending on which numbers we're plugging in, we may choose to use the first or the second option. So at point B, we're missing the height, and we want to substitute in t equal to 1. I think maybe using the first equation is easier for that. So the height at time 1 for point B is going to be given by negative 10 times 1 plus 80 times 1 plus 90. And so that's going to give us a value of 160 meters. So completing the table and completing the ordered quadruples on the graph, we have that the 160 meters makes sense for point B because it's somewhere between 90 meters and 250 meters. Okay, let's take a look at the next part of that question. We're asked in part E, why do we need an equation for the missing height data but not for the missing velocity or acceleration data? Well, if a value is constant, you don't have to do any guesswork. We just know that the value, like the acceleration, is always constant. In the case of the velocity, we can come up with these proportions or similar triangles because we have the linear relationship or constant slope in the velocity time graph. But when we have a nonlinear function, for example, a parabola graph, if you want to go from 0 to 4, let's say that we have a value here of 16, then the midpoint of 0 and 4 is 2, but on a parabola such as y equals x squared, when x is 2, the output is 4. And if we were being careless, or just assuming we had a linear relationship, we might try to take the midpoint of the two output y values, namely the 0 and the 16, and get an output that would lie on a line instead of the output that lies on the parabola. What I'm really talking about here is not having similar triangles available to us because we don't have linear functions. And so as soon as a graph or a function is not linear, we don't have proportions, and we can't really predict halfway points or quarter points by using proportions. So in this case, we do need the equation to definitely substitute in to accurately get the output values. Okay, so we had done almost all of the sketches for number 12. There is one sketch remaining, and this function here is the speed function. Speed is the magnitude of the velocity vector. And if we have a vector in 2 dimensions, we find magnitude by using Pythagorean theorem. When we have only 1 dimension, magnitude is the same as the absolute value. So speed in 1 dimension is the absolute value of velocity. And when we're finding the absolute value as a graph, we start off with the original graph, the velocity graph, and we perform the absolute value transformation, which is a partial vertical reflection. Remember, the goal of the absolute value is to make all of the output values positive or 0, to make all of the output values non-negative. So when we're looking at the different velocity values in green, we have some positive velocity values, a 0 velocity value, and some negative velocity values. What we want to do is reflect all of these negative velocity values vertically so that they become positive. So we are going to flip this velocity graph through the time axis so that we have no negative velocity values when we're done. And so we can do that by recognizing the same 3 points here. We have a 0, 80, we have 4, 0, and then we have negative 100, 90. But that negative 9. But that point is going to be reflected to 9, I said the ordered pairs backward here. It's going to be 9, 100. And so this is what we do when we get the modulus or the absolute value function. We're really performing a partial vertical reflection of the graph that was on the inside. Okay, so this is at 9, 100, and I'm just going to say that the velocity function is the absolute value of negative 20t plus 80. So now when we go back to our intuition, when I asked you to pause the video and to ask yourself, when is the object going up, when is the object going down, when is the velocity increasing or decreasing, when is the particle speeding up, and so on. I want you to try answering these questions again using the graphs, and then compare to see how you did. So now the object is going up for the time values of 0 to 4. So for time contained from 0 to 4, the object is going up, and then the object is going down for time contained from 4 to 9 seconds. The velocity is positive when the object is going up, so that's the same as time from 0 to 4. And the velocity is negative, so we can see here from the graph that the velocity values are positive from 0 to 4. And then from 0 to 9 seconds, the velocity values are negative. The velocity is increasing. Well, if we take a look at the velocity graph, we see because of the negative slope, the line is always decreasing from left to right as time increases, and therefore the velocity is never increasing. So we say time is contained in the empty set. Meanwhile, the velocity is decreasing on the entire time domain from 0 to 9. So this may have been different from what your intuition said, and partly that intuition is wrong because you may not understand the definitions of velocity and speed as well as you should. So the particle speeding up is really another way of saying when is the speed increasing. And now that we have a speed graph in the middle, we can say that the speed is increasing. I'll just write those words underneath. Speed increasing is consistent with the times from 4 until 9. And so we have time contained from 4 to 9 answering this question, and that's as the object is on its way down. So from the maximum height speeding to the ground, the speed is increasing. On the way up from time 0 to 4, the speed is decreasing, and we can see that the speed values, the graph is decreasing from 0 till 4 seconds. And then lastly, the acceleration is negative always, and so the answer to part A is t contained in the empty set, and t contained from 0 to 9 produces negative acceleration. So now just compare your answers to see how your intuition fared and to see if the graph helps you to understand things a little bit better. Lastly, we want to talk about anything we notice regarding the time-intercept value on the velocity and speed graphs. We know that that intercept value is 4, and that 4 value is not random. That 4 value, if we looked back to the vertex form of the height graph, we saw that it was the 4 was the time-intercept of the height graph. So if we go back to the graph with the ordered quadruples, we see that we have a velocity of 0 whenever we have maximum height. And that's corresponding to the time value of 4. So this is very interesting when we start to make some connections between height and velocity graphs to recognize that they are linked by the common variable of time. So the time-intercept on the velocity and speed graph is the same as the time to maximum height. So let's write that here. T equal to 4 is the velocity and speed time intercept. In other words, it's the time value that makes the velocity equal to 0, and it's the time value that made the speed equal to 0. Similarly, t equal to 4 is the time that produces maximum height on the height graph. And so there will be a lot of questions in physics, for example, asking about the maximum height, and one way to work that out would be to find a 0 of the velocity function. Similarly, in part B it says that what do we notice about the height values at times that have the same speed? So if we take a look at times that have the same speed, we really need to see speed as the absolute value of velocity. And if we have the same speed, that means that the velocity values could be the same or they could be different. On the way up, the velocity values are positive, and on the way down, the velocity values are negative. But if we take a look through the axis of symmetry at some symmetric points, namely points that have the same height, then we see at height 90 on the way up or on the way down, the velocity values are different. But the absolute value of those velocity values are the same. And so we see that at points that have the same height, going up and coming down, the speed values are equal. And so this has to do again with the symmetry through the axis of symmetry. In this case, the equation of it is t equal to 4. So just to put that recognition into an answer for number 15b, what we notice about the height values at times that have the same speed is that points or times with same speed, which means v up is equal to negative v down, implies same heights. And this is due to the symmetry of the parabola and all of the algebra that's related to the linear velocity and the constant acceleration functions. The last thing we're asked to notice is something about the velocity values at times that have the same speeds. And for times with the same speeds, two things could happen to the velocity. They could either be equal or they could be negatives of each other. And we've said that here. Velocities are either equal, not in this case, because in this case we only had two different velocities, or negatives of each other. So once we start to recognize these connections, we can use these connections in solving all sorts of problems. But for certain, the graphical approach and seeing all of this information, especially with 3 points, let's label them A, B, and C, points that correspond to launching, to maximum height, and to landing, are really, really crucial for fully understanding free fall motion. So hopefully this clears up some of the misconceptions you had in physics, and you can see it's a quick exercise to sketch the quadratic, the linear, the absolute value, and the constant function graphs to help understand the physics concepts a little bit better. That's all for now.